Hello everyone. Today we are going to discuss power system analysis and stability subject. So in VTU syllabus, this subject is taught in 6th and also in 7th semester. In 6th semester, the subject to be learned is power system analysis 1, that is power system analysis 1 will be learned in 6th semester, and in 7th semester it's continuation of power system analysis 1 and is named power system analysis 2. So it is briefly PSA 2, that is in the 7th semester. This video is introduction to PSA 1, and in this video we'll be discussing about a representation of power system components. A power system mainly consists of generating stations, transmission lines and distribution systems. Normally, when we are doing the analysis of power system, these components are written with the help of single line diagram. Let me show you a simple power system network. So let me write a generator, and this is a bus bar and a transformer. One more generator, bus bar and load. So you can see here, this is a generating station and this is a bus bar and this is a step up transformer, and this is from here to here, this is a transmission line, and this is a step down transformer, and we have one more bus bar and the load here I have taken motor as a load, and this is a simple power system network. Now before we understand what are the symbols used in the representation of power system network, we are going to study two very important terms. There is definition of symmetrical and balanced network. So symmetrical and balanced network. Let us see what is symmetrical network. So the term symmetrical tells you that when we see a network or power system from any phase, the impedance value must be same. Or in other words, if the impedance value of all the three phases are equal, then we can call such system as symmetrical system or symmetrical network. Or if there is any mutual impedance, the value of mutual impedances also must be equal. So we can represent impedance like Z, this is known as self impedance, so we can name it as ZS. So all the three phase self impedances must be same. Okay, and mutual impedances can be represented with Zm. So I'll define again what is symmetrical network. So symmetrical network is a network when it is viewed from any phase, the impedance value must be same. So the second definition what we have to see is the balanced network. Balanced network or balanced system. You know that in three-phase system we have three voltages, three phase voltages and three phase currents. So a balanced system is nothing but the three voltages or currents must be equal in magnitude, must be all three voltages or three currents must be equal in magnitude, must be equal in magnitude and have the same angle difference between them. That is, we know that usually a balanced system has angle difference between the phases as 120 degree electrical. So if a system is balanced system, the three voltages should have same magnitude, or if it is current, three currents should have same magnitude, and they should have angle difference between them between the phases as 120 degree electrical. So for planning the operation, improvement and expansion of a power system, it requires analysis of the system. So this requires modeling of the system. So we need to know how to model a system, then by we can analyze the system. Actually, analysis is nothing but, so analysis of power system. Power system is nothing but finding out the value of voltages and currents, and thereby we can also calculate the value of power. So in order to do the analysis of power system, we need modeling of power system. Modeling of power system. So to write modeling of power system, we need to know what is the circuit diagram of each and every component used in the system. We know that there are various components used in power system. There are generators, there are transmission lines, there are transformers, there are loads or motors or lighting loads, different loads. So we have various elements in the power system, and also we know that all these elements appearing in power system are three-phase components. So in order to write the modeling, it will be very difficult if you are using three-phase equivalent circuit of the components. So what we have to do is, we have to write a single phase equivalent circuit of all these elements. Whether this is possible? Yeah, surely it will be possible, because whatever analysis we are doing, we are taking for three-phase balanced symmetrical system. Three-phase balanced symmetrical system. So if it is a symmetrical balanced system, we know that all the three phases should have, should have same impedance, and also we know that since it is balanced, the voltages and currents should have same values. So we can convert a three-phase balanced symmetrical network to single-phase equivalent circuit. Thereby we can do the analysis. So to write the modeling or equivalent circuit of three-phase system or single-phase equivalent circuit of three-phase system, we need to know the equivalent circuit of each and every element in the system. Equivalent circuit of each and every element or component of the system. So let us see the basic components of the system and their single phase equivalent circuits. So in order to write the single phase equivalent circuit of the system, power system, we need to know basic four components and its equivalent circuit, that is single phase equivalent circuit. So the basic four components are generators, also known as synchronous machines or synchronous generators, and we have motor at the load side, so it is load, and we have transformer. Basically we will be using two winding transformer equivalent circuit. So the fourth one is transmission line. So let us see one by one what is a single phase equivalent circuit of all these components. So first one is generator. So three-phase equivalent circuit of generator, can be written like this. So where we have three phases and we have three-phase impedance. So one is ZA and ZB and ZC. All these are phase impedances. And also we have the generated EMF. So it is represented as EA, EB and EC. That is first, second and third phase. So since it is a generator, current will be always going out or away from the generator circuit. So we have current going out, which is first phase or IA phase, IA current, IB current, that is a B phase current, and also we have C phase current, IC. Now we have to represent this as single phase equivalent. That is possible if and only if we take a symmetrical and balanced circuit. Symmetrical and balanced circuit, and we know what is the condition for this. Yeah, fine. So this can be represented as a single phase equivalent circuit as with the one impedance which can be given as ZS, and one EMF which can be given as the EG, that is EMF generated in the generator circuit, and one current, that is IG. So this is the single phase equivalent circuit of the generator. Next, let us see the single phase equivalent circuit of motor. So I have written here. So this is a three phase circuit actually. So three phase circuit for synchronous motor. Synchronous motor. So the basic difference between the generator circuit and the synchronous and the motor circuit is we have current coming in motor circuit and current going away from the generator circuit. So here, since it is a motor circuit, I have written current coming into the motor circuit. Otherwise, it is same as the generator circuit. We have the impedance for each phase. So we have ZA and we have ZB and we have ZC. And an impedance, we know that impedance can be represented as a resistor and a reactance. So Z can be represented as resistor and reactance X, depending on which type of impedance it is. If it is inductive impedance, then Z can be written as R plus JXL, RL plus JXL, or if it is capacitive, then we can write impedance as R minus JXC. So that depends on which type of winding it is. Okay, fine. So now the equivalent single phase circuit of this particular component, that is synchronous motor, can be represented as, so impedance, that is again a resistor and reactance. So I can write this as ZS, or you can represent it as a ZM also. So we have EMF, that is back EMF. Since it is a motor, it is back EMF, and I can represent this as EM, and we have current coming into the motor. So this is IM. This is IM. So this is a single phase equivalent circuit of motor. This is three phase equivalent circuit, and this is a single phase equivalent circuit of motor. And the next very important component is two winding transformer. So this itself is a single phase equivalent circuit, because it is very difficult or complicated to write three phase circuit of transformer. So this is a single phase equivalent circuit. Let us see what are the notations used here. So V1 as a primary side voltage, V2 dash is secondary side voltage. Why it is V2 dash? Because we have to take care of the voltage transformation ratio. So V1 is primary side voltage, primary side current as I1, R1 as primary side resistance, X1 as primary side reactance, and R2 dash is secondary side reactance, which can be given as R2 by K square, where K is N2 by N1, or it can also be written as V2 by V1, and this is known as voltage transformation ratio, or just transformation ratio. So basically transformation ratio depends on what is a primary turn and a secondary turn, and also it depends on the voltage, primary and secondary voltage. Okay, fine. So along with this we have one more circuit here, that is the exciting circuit of the transformer. So we have R naught as exciting resistance, and this is exciting reactance. So this is the basic single phase equivalent circuit of two winding transformer. And the last component is, what we have is transmission line. All these are basic components. There may be some other components also, but which are not very useful for us to do the analysis for theoretical purpose. So we write only generator, motors, and two winding transformer, and also transmission line. So for transmission line, normally we can represent it with nominal pi method. There are two methods, nominal t method and nominal pi method. So, but normally we use nominal pi method for the representation when we do the analysis of power system. So this is how we write. So we have Vs on one end, that is Vs is sending end voltage, and we also have Vr on the other side, that is the receiving end voltage, and in between we have a series impedance. This is series impedance, and we have Y as total shunt admittance, and since it is pi method, we have HLC, that is half line charge admittance, or it is Y by 2 on both the ends. So Y by 2 on one end and Y by 2 on other end, where Y is the total shunt admittance. So all these are basic components, and they are single phase equivalent circuit. So to do the analysis, we have to connect all these single phase equivalent circuits of the components, and we can calculate the voltage and currents. So the next topic is per unit method. And so the per unit method and the power system analysis continuation we'll see in the next video. Thank you.